All right, this is part 3 of our lesson reviewing the polynomials unit. In this lesson, we're going to start off talking about the zeros. It's all about the zeros, finding the zeros. Starting with just the possible zeros using what we call the rational root theorem. But I think we'll go ahead and get into finding the actual zeros. Okay? All right. Well, let's start with number 18. Okay, when we talk about the possible rational zeros, the numerators, the possible numerators, all come from the constant term. All right, so the possible numerators, in fact, hold on. I'm going to put n here for numerator, d here for denominator. The numerators are all going to come from the constant term, the 2. What are the factors of 2? Yeah, just 1 and 2, all right, are the only things that 2 is a prime number. Okay, but the denominator is even simpler than that because the denominator comes from the leading coefficient. What's the leading coefficient? Leading coefficient is 1. Okay, so the only factor of 1, of course, is 1. So to get the possible zeros, we're just going to mix and match these numerators with this denominator. So it's going to be a really short list. All right? The possible zeros will just be 1 over 1 and 2 over 1, or 1 and 2. And don't forget they could be plus or minus, though. So plus or minus 1 and plus or minus 2. So, but of course we're not done, because if you read the directions carefully, as I always do, it says the list of the possible zeros, but then use synthetic division to find all the zeros. Okay, so we got to use some synthetic division. So let's just go in order. So if I do my synthetic division, I would start with 1. My coefficients here are 1, 4, 5. Be careful that none are skipped. You know how that happens sometimes? So don't forget about that. 1, 4, 5, and 2. Okay, so we can use synthetic to find out if this works or not. Okay, so the first one you just bring it down. 1 times 1 is 1. That makes 5. 5 times 1 is 5. That's 10. 10 times 1 is 10. That's 12. What should happen here if it's a 0? Right? If 1 is a 0 of the function, what should I get for the remainder? I should get 0. So 1 was not working. All right, so I got to keep going. So this time I'll try negative 1. Okay, 1, 4, 5, 2. Okay, so that's going to be negative 1, 3. 3 times negative 1 is negative 3. 2. 2 times negative 1 is negative 2. That does make 0. So that means negative 1 is an actual 0 of the function. Notice I'm not using my TI-30XS multiview. That would be cheating right now. All right? But I don't need to do any more synthetic division after that. Once I get it down to a trinomial, I can like factor or use the quadratic formula. Do you know what I mean? If I put the variables back in, do you remember that this makes x squared plus 3x plus 2? Why did I put it 2x? Plus 3x plus 2. And let's try to factor this. So that would be x, 2, and 1, plus and plus. So how can I use this to get the zeros? Set them equal to 0 and solve. So, you know, if you do x plus 2 equals 0, you're going to get negative 2 for the 0. If you set x plus 1 equal to 0, you're subtracting 1 from both sides. Oh, well, we already have negative 1. Yeah. All right, it must be a double. So these are the actual zeros. All right, so for the possible rational zeros, remember, it's all about the numerator as opposed to the denominator. Now, the numerator is always going to come from the constant term. So that makes it simple because the constant term is just 1. What are all the things that can divide evenly into 1? 1. So that means that's the only possible numerator. Now the denominators come from the leading coefficient. Okay? So the denominators all come from 4. All right, so what are the factors of 4? Well, smaller. 1, 2, and 4. Okay? So the possible zeros are what you get when you mix and match the numerators with the denominators. Well, there's only one numerator, so it makes it easy. So it's just, I'll simplify it later, but it's just 1 over 1, all right, my numerator over the denominator, 1 over 2, and 1 over 4. It's my only numerator over all of the various denominators. So tell me why I would not get full credit if I put 1, 1/2, and 1/4. Why did I just get half credit just now? Yeah, because they're all plus or minus. They're all plus or minus. Okay? So that's it. Those are the possible rational zeros. That doesn't mean they're all zeros. It just means that they're the only ones that are like even fractions. Any other ones would be irrational or imaginary. Now, we're supposed to go on from there and use synthetic division to find all the zeros. So right now, we're not supposed to be using the fancy features of the TI-30XS multiview. No table function right now, okay? So instead, what we're supposed to do is, hopefully it'll either be 1 or -1, because up until now, we've never had to do it with fractions. Synthetic division, it's possible, but let's hope to avoid it. So let's try 1. Let's try using 1. Okay, so I try 1. Let's see, no terms are missing. So here we go. 4, -9, 6, and -1. Remember how synthetic division worked?
3 and a 4, multiplied by 4, that's 4, -9 plus 4.
You got it. So 4 times 1 is 4. That's -5. -5 times 1 is -5. That's +1. Uh-oh. 1 times 1 is 1. 0. Okay? That means that 1 is an actual 0. All right? We got lucky. The first one we tried actually worked. So there's a little line for us to write down all zeros. Now, these aren't possible zeros. These are the actual zeros of the function. Okay? So far, we found one of them. All right? The 0 is 1. Okay? Now that we found one of them, I don't need to do any more synthetic. How can I find the other? By the way, how many zeros are we sort of expecting?
3.
We're expecting 3. How did you know that? Based on what, though? The exponent, the degree. Okay, when the degree is 3, if you count repeated zeros and imaginary zeros, there will be 3. There will be exactly 3 if you count the repeated ones and the imaginary ones. Okay, so we found 1 so far. How will I find the other 2 without doing more synthetic division? Go, Bonnie. Let's see, plug into the calculator. Is there a way to do it without the calculator?
No.
Because you never know what I'm going to do with that calculator. Worth, go.
You need to factor the trinomial.
Factor the trinomial, okay? If we put these variables back in here, then that's going to be, remember, 4x squared minus 5x plus 1 is the trinomial based on those remaining coefficients. And so now we will try to factor this to find the other zeros. 4x squared. Maybe it's 2x and 2x. If this doesn't work, I'll go back and try other stuff. 4 and 1. So if I go 1 and 1, that's not going to, I can already see it's not going to work. Inner 2, outer 2, that's only 4. That's no good. So let me go back and try 4 and 1 instead. Okay, so 4x and x. Now inner is 1x. Outer is 4x. Inner plus outer must equal middle. I want a middle of negative 5. So if I had negative 1x and negative 4x, that would make negative 5. So that means both of these would have to be negative. And also it gives me positive 1, since a negative times a negative is a positive. So there we factored it. Now how can I use these factors to get my remaining zeros? Tell me what you're doing.
Setting is equal to 0.
Yeah, you're setting these factors equal to 0, right? So you're going 4x minus 1 equals 0. Then that would be 4x equals 1. X equals 1/4. So that's a 0. Notice, looking back at the possible zeros, was that one of them?
Yes.
Yeah, it's right there on the list, as it should be. As it should be. And then what's the other 0?
1.
The other 0, well, you know, it's probably the same. We already had it listed, so we don't need to list it again. It's a double. That one's a double root. All right, so that's it. Okay, so those are all the zeros of this function. So there are only 2. It looks like we're missing one, but it's because this one's a double. It was like if you factored it, it would be 4x minus 1 times x minus 1 times x minus 1 again. It happened twice. All right, moving on. So that was it for number 19. Yeah, so end behavior is what's happening on the ends of this graph. What's happening on the left side, you know, because over here this is the left, and what's happening on the right-hand side. Over here this is the right. So end behavior always starts off the same way. This is the side that means left, because it says as x approaches negative infinity. That means on the left side of the graph. And f of x is like the y value. So on the left side of the graph, what happens to the y values? Well, as we go further to the left, the y values go down, down, down. So that's why we put negative infinity, because it's falling. What happens on the right-hand side of the graph? You know, I'm going to the right. I go up, I go down, I go up, but in the end, I go down, down, down on the right. So I'm approaching, the y values are falling towards negative infinity on the right-hand side as well. All right, so it's like falling, falling. Negative infinity on the left, negative infinity on the right. Okay, so that negative infinity is the one that's on the left. This one is the one that's on the right. All right, it's very glitchy today. Okay, is the degree even or odd? Just say this verbally. Is this even or odd?
Even.
How do we recognize an even degree function?
Wait.
Say it again. How do I know if it's an even degree? I mean, oh, well, yeah, how do I know if it's even or not? Well, let's be careful, okay? Because we've talked about 2 different kinds of even. There's an even function, which is very specific. It has to have y-axis symmetry, all right, which this does have, so that makes it an even function. But then there's even degree. Okay, even degree just has to do with if we wrote the function down, what would be that highest exponent? It doesn't even mean it has to be. It doesn't even have to be y-axis symmetry for even degree. Okay. So this one has even degree. See how both of the arms are sort of pointing in the same direction?
Yeah.
All right, that's the key. Let's see.
So that's like the part like.
Just remember, for example, if you have a function like f of x equals x squared, what does that look like? Just a rough sketch. What does it look like? A parabola, okay? All right, now how did I know it was going to be an upward-facing parabola, by the way? Because it's positive. If I did f of x equals negative x squared, okay, why did I almost do it the same way? 2 hours of sleep, that's why.
Mr. Bro, you need to get more hours of sleep.
I know.
Please promise me that you're going to sleep more over Christmas.
Oh, yeah, I'm going to sleep every day. Sleeping every day. Okay? So what we learned was look at the end behavior. Okay? When it was positive, both arms are pointing up. When it's negative, both arms are pointing down. All right? But either way, both arms are pointing in the same direction. Okay? What we learned was all even degree functions have the same type of end behavior. Okay? So for example, say if I had x to the 4th power plus whatever, 3x squared. I'm just making stuff up now. All right, plus x. The degree of this is 4. So just like a x squared is a parabola, this is going to have a similar end behavior. Now granted, it makes a W shape, not just a smooth parabola, but still, look at the arms. Just like a parabola has both arms reaching toward the sky, a 4th degree has both arms reaching toward the sky. Okay? And if I made it a negative leading coefficient, what would happen?
Facing down.
It's facing down now. Okay? So just instead of a W, it'd be more like an M. Okay? And so, look, let me just skip way ahead. Say if I had x to the 8th power, I'll say 3x to the 8th power plus blah, whatever else I had, doesn't really even matter, plus 5. Okay? Show me with your arms what the ends of this graph would be doing. Show me with your arms. Would it be going like this, or like this, like this, or like this? All right. Simple's frowning. All right, put your arms down. Okay, people watching the video, you couldn't tell, but everybody, I'm like going into the video. They're going like this. The video, y'all can't see me. All of their arms were in the air like they were, under arrest. Because yes, just like a parabola has its arms facing in the air, any positive even function is going to have its arms facing in the air. All that's going to change, there'll be more waves in the middle. But in the end, the arm's facing the air. Okay? And if it were negative, it would be like arms facing down. All right, so that's how you can recognize an even degree function even without an equation. If you see both the arms going in the same direction, it must be even. Because what does it look like when it's odd? Okay, when it's odd, we started with this. Okay, when we had x to the 3rd power, what does that look like? What letter? There's like a letter we would use. Yeah, like our basic model for a cubic function would be an N shape. Okay, instead of a parabola. And if we had a negative one, what happened?
It would be opposite of that, so we.
Yeah, it'd be opposite. It'd be like an upside down N shape. Okay? And because of that, all odd functions have the same type of end behavior. So if I had a function that was x to the 5th power, plus whatever else, it doesn't really matter. But that 5th power makes it odd degree. It will have an extra bend in it, but look how the end behavior is the same as a cubic function. Nah, don't do that. Okay? So that's what we mean when we talk about even degree. Just looking at which way the arms go. All right, there is no neither. There's not an option. The degree is either even or odd. That's the only choice. Okay, now the very next one says, is it an even function, an odd function, or neither? Now what are they talking about? It's different. Yeah, now we're talking about the symmetry, okay? So now it could be even, odd, or neither. So it had to be an even degree function, but does it have even symmetry? Yeah, because it has y-axis symmetry. The y-axis splits it right down the middle. All right, so even. It has even symmetry as well. All right, this leading coefficient, positive or negative?
Negative.
Is negative because look how the arms are facing down. That's what a negative leading coefficient would do. Yeah, that's some glitchiness right there. All right, how many real zeros does this function have, and how do you know?
When it touches the x-axis.
The real zeros are where the graph touches the x-axis. Okay, so there's a real zero here, and there's one here. So there will be two real zeros. Let's see. How did you know? X-intercepts. Okay? Give the interval using interval notation where the function is less than 0. All right, I'm going to pause the video for a second because I want you to do this by yourself. All right. It's saying where's the function less than 0? So if we're talking about less than 0, we're talking about below the x-axis. So looking at this highlighting right here, that's a big highlighter there. This is the part of the graph that is below 0, less than 0. So those are the pieces that I want to capture with my interval notation. So that's why, like Trey was saying, I'm going to need the two branches. Now we're talking about x values when we do this interval. This piece on the left is from negative infinity to negative 5. Okay, look at where it touches the x-axis, negative 5.
Oh.
Okay, so negative infinity to negative 5. Okay. Round parentheses. We don't want to include negative 5 because right at negative 5, that's where it equals 0. Look at the statement. It doesn't say where does it equal 0, just less than. If it had been less than or equal to, then I would have used square brackets to include it. Keep that hat off your head, Matt. Crazy guy. So, union symbol. And then the right-hand side picks up here at 5 and goes from 5 to infinity. Okay? So people that didn't have it, do you understand now that you see it?
Yes.
Okay? That final exam is coming up like a monster.
Say a different word.
Like a
What word would you use? It sounded like a different word.
All right. One second. Look at number 21. How many roots does this function have? How many roots does this function have?
3.
Divided by 7.
2. 2.
3.
3. But 2 are imaginary.
This function has 3 roots. Okay? Because it didn't say how many real roots does it have. It just says how many roots. Okay? If I had asked you how many real roots, what would you have said?
1.
It only has one real root because that's the x-intercept. But looking at the degree, this function is degree 3. So it must have 3 roots. All right? Even if they're imaginary and such. All right, so now we have to find all the roots of the function. So we see one of them right there. All right, what's the one root that we can just see easily? Yeah, it's clearly right here at 3. Okay, so let's go ahead and write that down. With a root of 3, that gives us a factor of what?
X minus 3.
Right. It must come from a factor of x minus 3. Because you know how we set these factors equal to 0 to find the roots and stuff. Eileen, keep your head up. Sit up.
Come on, Eileen.
That posture is not acceptable. Okay, now how am I going to find the other? How do I find the other 2? Synthetic division, I heard like 3 people say. Okay. Synthetic division. So let's see. Do I have space for that up here somewhere? So let's take our one root of 3 and do synthetic division with it.
Oh, can I do that, Mr. Bird? Of course.
Now we're running low on time, my brother.
Why is it 3? Because it's the root.
So
It's the root that we found. It's the x-intercept off the graph. Okay.
bring your 1
All
down,
right.
Mr. Bird.
Yes, sir.
Bring the 1 down, you're gonna get 3, negative positive 2, 6, 7, 21 positive 21, then equals 0.
Okay, and it better because it on the graph it showed it to 0, so it should definitely give us 0. Oh, it's just getting ready to say Jorge. Now, how do I go from here to find other stuff? Factor. Okay, Peta. Good job, Peta. We take this, and if we put those variables back in there, we're looking at x squared, all right, from the 1, plus 2x, plus 7.
You do quadratic formula, Mr. Brown.
Yep, you have to.
Oh, garbage.
This is rubbish.
Well, we knew we'd have to do the quadratic formula because otherwise we would have seen it on the graph.
Trying to set me up.
Okay, so yeah, let's do the quadratic formula. Or we could complete the square, but y'all never remember that.
That's very true.
Very true. So we
Mr.
will.
Brown, you guys take those things off
Yeah, you
for the
did.
final or no?
Remember, b squared minus 4ac.
Be there, be square.
Always start with the b squared minus 4ac part. So that's going to be 2 squared minus 4 times 1 times 7. Now, I didn't really need to write the 1 down.
Nope, Mr. Brown.
I'm just being thorough.
Negative 24.
Okay? So this is just 4 minus 28. So that's going to be negative 24. Okay? Now we can do the rest of it. So x equals opposite of b. So that'll be negative 2 plus or minus square root of negative 24
Over 2.
over 2. All right? It's all over 2a, but, you know, a is 1. See that negative under the radical? What do I do with that mess?
You do the I, Mr. Brown. I.
You do I. That's correct. So we have negative 2 plus or minus I
24.
radical 24
Yeah, I know. Why am I still feeling
over
this
2.
place?
So the square root of 24,
Is
all right, I'm going to cheat and use my calculator right now.
Peter.
square root of 6 minus 1.
Okay, it's 2 root 6. 2 root 6. Okay, so we get x equals negative 2 plus or minus 2i root 6 divided by 2. Now, is that my final answer?
No.
What can I do now?
Put it, plug it in as a plus and plug it in
Plus
as a
and
minus.
All right, do you see how all 3 of these are divisible by the same thing?
They're in love.
Yeah.
What am I going to divide by, obviously?
2.
All of these are divisible by 2. It's all or nothing. You can't just do 2 at a time. It's got to be all 3. That's why I use the heart to remind me that's got to be all 3 or nothing. So that's going to give me negative 1 plus or minus I radical 6 over 1, which I don't need. So these are my other 2 zeros, the ones that we couldn't see. Let's see, negative 1 plus or minus I radical 6. So negative 1 plus or minus I radical 6.
What if you like solved it out?
1 second. All right, this video is getting long, so I'm going to have to stop this video here.
Class is over.
And we'll pick up from here on the next video. All right, I forgot one thing. Factored form. I sort of skipped over that. So we have these zeros, and we have our first factor. But because we couldn't factor any further, we have to figure out what the other factor is going to be. And it's right here. This trinomial that could not be factored, since you can't factor it, that's what you write down. X squared plus 2x plus 7. Alright, and that's what you would put for a factored form. Don't do anything crazy with this I business. This is what you put.